Welcome to Unit 12. It's another unit on extremization, and we focus mostly on global aspects. And I want to start with an example just to review the second derivative test. This is a function f of x. In order to find maxima and minima, we look at critical points. So that's the places where f prime x is equal to 0. In this case, it's 15x to the 4 minus 15x squared, which is 15x squared times x squared minus 1. And you immediately see that what the critical points are. They are 0, 1, or minus 1. So if we want to draw this function, actually we have also an interval given where the function is kind of considered. So we have from minus 1 to 1. And then we have the interval is given from minus 1.4, which is here, from here to here. So that's the interval where we consider the function. Let's just see. If you look at this function here, you see that there are roots at x equal to 0. There are roots also, so there are roots at x equal to 0. And also there are roots at square root of 5/3 or minus square root of 5/3. So that's the question now, where are these roots? In this case, I think it's above that here, and here it's below. So it's kind of, these are the roots here. Let's just see, these are roots. It just shows this numerically so that we are here. And then we have here the critical points. We have also learned from the second derivative test that we have to look at the second derivative. So let's look at the second derivative. f2 prime x is 60x to the 3 minus 30x. And in this case, at 1, this is equal to 30, so that's positive. So the second derivative here is positive, meaning that it's concave up. And here the second derivative test, because at minus 1 gives you actually here a negative value. So this is f2 prime is negative, which means that it's concave down. And so the function kind of has to have a maximum here. So the only possibility is that we have a maximum here. Then it goes to 0. And it is has quite a flat 0 here. Actually, the second derivative is 0 here. This is also a critical point. But f2 prime x is equal to 0. So it is very, very flat here. And then we have a minimum, and we are going through here through. So let's look at this. That's essentially the. Let me just make it yellow here. That's the function. We have a pretty good picture of the function. So these are the critical points. This is a minimum, local minimum. This is a maximum, local maximum. And this is an inflection point. This is a point where it changes from negative to positive. So this is a critical point which is undetermined, which is not covered by this second derivative test. So it's neither maximum nor minimum. Neither max nor min. Now, what is new in this lecture, we also look at the boundary points. So in this case, the boundary point is actually, we are cutting it off here. We just that's the place where we cut things off, and we are looking at the values which we get. So we have to do that numerically. We have to get the values to actually see what is the global maximum. So for the overall maximum, that's what we do then here. For the overall maximum minimum, we have to look at the critical points, global max or min, look at with the critical points, the values at critical points, and boundary points. So for that you usually then, in this case we need a calculator to see or graph it, and we actually see that this is still this is the global maximum here. So this is the global max. That's the overall largest point in this landscape here, while the global min, if I'm right, so I have here the graph. So when I draw it, this is a little bit lower here. So this is actually the global minimum. In this case, it was a boundary point. We didn't really have a critical point here. So there's, the slope is not zero, but we are at the boundary. So we are stuck here at the boundary. That's our global minimum on that interval here. So that's a very important example. It kind of, everything comes together. We have minima, we have maxima, we have this case where we don't, the second derivative test doesn't apply, and we have boundary points also which matter. Okay, I have here the definitions of global maximum, global minimum. It's a very intuitive notion. It's sometimes also called absolute max. But I'm avoiding this because absolute max could also kind of be associated with absolute value or something. So global maximum, global minimum is a better word. And there is an important theorem which is due to Bolzano, and it's called the extremal value theorem. So if f is continuous, we don't even need differentiability. But it's given on a closed interval. It's important that we have a closed interval. Then f has a global maximum and a global minimum. On A bit. In the notes I give you an argument for the proof. It's not completely obvious, but it's a beautiful result. It leads to real analysis. So Bolzano was one of the first who really saw the need to build up a theory like that. And it's very important in economics these days, such considerations. Okay, let's look at the problem of maximizing the area of this stadium, Harvard Stadium. We have 40 minus 6 here, the length here, 2x here. This arc has length pi x. But the area we can compute with the radius x here. The area is a function which we have to extremize, is pi x squared half. And then the rectangle area is 40 minus 6 times 2x. So what that is, that's just pi. And let's double check this. So this is the x squared. We have minus 2x squared, that's also minus 2x squared here. That's right. So we have to look at the critical points. So that's pi minus 4x plus 80. This is equal to 0 for x is equal to 80 over 4 minus pi. So 80 over 4 minus pi, what's that? I have to look that up. So now it's actually quite interesting here. So we have on that interval where the function is really defined. So it is defined from 0 to 40. So it's defined from 0 to 40. Otherwise the area would become negative, right? So that is the whole thing which makes sense. So this is bigger. So what actually happens is the function has not yet peaked here at 40. So we might look in the lecture at some other parameter. So in this case, the global maximum is actually here at the boundary and not at the critical point which we have. So this is not the maximum because it's outside the range. So we will see if you make the stadium smaller, if you make this smaller here, then there will be actually a maximum which is, and for smaller, so we will have a situation where it is where it has peaked before. In this case, it peaks after that. 93 is bigger than 40, so it's outside the domain where we really kind of where it really makes sense. Very nice problem. The next problem is a very classical problem. I learned it as a student myself, maybe with a flagpole. Usually it has been asked with a Statue of Liberty. So here this is the Statue of Liberty, and we have an observer is here. So this is an observer here, and you are observing the Statue of Liberty or any statue, and I actually take the Harvard statue, and this is John Harvard. I'm using this since 10 years as an example, and this is a tourist, right? Tourist, this is you, and this is the John Harvard statue. And then what happens is we want to maximize this angle here. So this angle, maximize the angle. Actually, we take this is f of x, and what we have here is x. So in which distance from the Harvard statue? Just draw that. Sitting here, and with a golden shoe. Golden shoe which you have to kiss to get into Harvard, right? That's the thing. It's not enough to touch it. You don't get into Harvard when you touch it. You have to kiss it. It doesn't matter whether you get diarrhea afterwards for a week, but you have to kiss it. And but that's, you want also to make a photo of the statue. And what happens is you want to, if you are very far away, of course this angle is very small. You look at the statue from very far away. But also if you are just below the statue, you see also a very small angle. You don't really see the statue well. And so there is an optimal distance where the angle is maximal. So depending on the distance. So the function is, what we have to do is we have to take this angle minus this angle. So and actually I also we give the dimension. So the dimension here is 4, and this is 5. So the total height is 9 feet here. This is 5 feet. This is 4 feet. So what we have is we have this angle here. So this angle, let's call this alpha, and this angle, call this beta. So f of x is equal to beta of x minus alpha of x. Right? The bigger angle minus the smaller angle. The bigger angle is the arctan of 9 over x. And then minus the arctan of 4 over x. So that's our function. That's the function we want to extremize. And it makes sense for x positive. X can become arbitrarily large. There's no boundary. But so this is a little bit the challenge, right? But how do we differentiate the arctan? And the last week, we have covered the chain rule, and we have learned how to differentiate that. So we have learned how d over dx of arctan of x. That's 1 over 1 plus x squared. Just put it as u. And so that's what we can use this, and then we get f prime x is actually minus 9 over x squared by the chain rule over 1 plus 9 over x squared, and then minus 4 over x squared over 1 plus 4 over x squared. So this can be simplified a little bit if you do that. Let me just see. We will do that. I will do that maybe in class in detail. It simplifies to, so this is equal to 5 times 36 minus x squared. And then on the bottom we have 1296 plus 97x squared plus x to the 4. So there is no big magic here. We just multiply out, make a common denominator, and we get this. But you see that what is the extremum? The extremum is when we have x is equal to 6. So x is equal to 6 is the optimal. So this function which we have goes from x equal to 0 to infinity. It starts at 0, optimized at 6, and then goes again to 0. So there is just one global maximum, and that's x equal to 6. Cool. So that's it for today.